Okay. 4.7 is all about inverses. So first thing I want you guys to do is look through these three functions here, and I need you to know well, what the equations are. If these are parent functions, can you write me an equation for each of these? Y equals, it's just going to be something x. I just need you to know whether it's sine, cosine, tangent, secant, cosecant, or cotangent. You guys write me some equations for these three. What you looking for? Huh. I don't think, is anybody? Yeah. Someone's out. Someone's got it. Who sits there? Henry, thank you. All right, how we doing? Were you guys able to recognize that this is a sine? If it's not shifted at all, it's a sine. It's going through the origin, right? This one is not going through the origin, starting at a max. Were you able to recognize that one as the cosine parent? And this was a new one for us last time. I need you to know that this is what tangent looks like. Tangent x. And if they are parent functions, then we should be able to label some of these x values. So a period of sine starts and ends at an x-intercept. And how long is a period of sine and cosine, by the way? 2 pi. So go ahead and label this 2 pi over here. And we might as well do that for cosine as well. So this would also be 2 pi. And let's go ahead and label the rest of them. So that would make this pi. That would make this pi over 2, and that would make this 3 pi over 2. And man, I got to write really tiny to fit that in. And just for fun, let's go ahead and label this negative pi over 2. And actually, that labeling is going to be the same for all three of these. We don't need to write them all, though, because if you look down at the next set of graphs down below there, I've already got the x-axes labeled for you. They're all going to be the same. All right, so I told you we got to review some cool stuff from first semester. Do you remember that trick you learned back in Algebra 1 to determine if something was a function or not? Vertical line test. Look through these three graphs and tell me, are they functions or no? They better be. We've been talking about trigonometric functions the entire unit, right? They are all functions. They all pass the vertical line test. Do you remember the visual test for testing whether a graph's inverse is a function? We do a horizontal line test for it. So look at these three graphs and tell me, are any of their inverses functions? All right, now that's a problem because we want to be able to talk about the inverses of sine and cosine and tangent, but we want to be able to talk about them as functions, and these are clearly not functions. Okay, what that means is we're basically going to need to do a little bit of mathematical trickery because we can't just like not do this. What we're going to do is we're going to just chop off a portion of each of these graphs, focus our attention on just one small portion, and make sure that for that portion, it would pass that horizontal line test so that its inverse would be a function. So I just heard a suggestion we could just do a period. Let's see if that would work. If I just did a period here, is my inverse going to be a function still? No, that's not going to work. I heard a half period. Is that going to work? No. And we're missing, and well, we could do a quarter of a period. Now that would pass a horizontal and a vertical line test, but it's not getting us the whole swing of the function. I get the kind of the upswing, but not the downswing. On the other, this quarter here. From where to where? Give me some values. Negative pi over 2 to positive pi over 2. Ooh, that gets me my positive piece and the negative piece. And it would pass both horizontal and vertical line tests, right? So that would totally work. Where would the next place we could do that be? We'd go from 2 pi. What about here? From pi over 2 to 3 pi over 2? That would work too also, wouldn't it? Now, if you were in charge, say it's like 200 years ago, or I don't know how long ago somebody decided this, but if you were in charge and you got to choose between this little piece of it here to represent sine, or this piece of it over here to represent sine, which one would you pick? The first one, because why? Because negative positive, the origin is in there. Yeah, you would pick the first one. That's what they picked too. You guys see, you could have written the book on this. So the way that we get around this whole idea so that we can make sure that our inverses are a function is we're going to just chop off a little piece of it. So for sine x, if we want to start thinking about the inverse, we are going to only worry about sine, the portion of sine that goes from negative pi over 2 to positive pi over 2. That works for us because it captures the essence of sine, right? It's got the negative part, it's got the positive part. And we're showing the origin here. Now look at cosine and tell me, what would you choose if you had been in charge when they arbitrarily picked how they were going to chop up cosines so that we would still keep the negative part, the positive part, but our inverse would be a function also? Where would you chop it? Can you set that aside for right now, please? Thank you. I'm here negative pi over 2 to pi over 2. That one's going to give me the origin, but it's only giving me the positive part. And yeah, we're not passing horizontal line tests. 0 to pi would be here to here. We like that. It does include the origin. We got the y-axis in there. It is giving the negative and positive, and it passes both the horizontal and vertical line tests. Yep, that's exactly what they chose. So cosine, when we start talking about inverse cosines, we're only going to be talking about angles between 0 and pi. Look at tangent, see what you would choose for tangent. We need to capture positive and negative, but we need to limit it somehow so that when we do the inverse, it would pass a horizontal line test so that the inverse is also a function. Where would you go on tangent? What would you do? Between the asymptotes, so negative pi over 2 to pi over 2 again? Yeah, that keeps our origin, that keeps some positives, keeps some negatives. And that is exactly what they decided to do too. You guys are so smart. All right. So we are restricting something about those. I should write negative pi over 2 to pi over 2. We're restricting something about our original functions. Are we restricting the domain or the range of the original functions? We're restricting the domain of the original functions. But you guys, we talked about inverses way back in chapter 2. What happens with domain and range when you get inverses? They flip-flop. So when I tell you that we're only going to look at sine values from negative pi over 2 to positive pi over 2, that tells us when we get to our inverses that our outputs are only going to be between these values. When I take an inverse sine, I will never get an answer that is less than this, and I will never get an answer that is greater than this. It's always going to be in between here. So what we're really doing is we are limiting, and this is down at the bottom of the page, we're limiting the outputs of our inverses. So we're going to go ahead and sketch our inverse trig functions here. So when we do this, you'll notice that the scale has just kind of flipped, right? Now my y-axis is in terms of pi, and my x-axis is in terms of, well, integers. So I'm going to just look point by point. Notice that the origin was on our original, so the origin should be on our inverse also. This point right here is at pi over 2 comma 1. I'm talking this point right here. So flip those around, that would be 1 comma pi over 2. This point down here was at negative pi over 2 comma negative 1. So flip it around, that's negative 1 comma negative pi over 2. And when we sketch this, remember how sine and cosine kind of level off at those points, at those maxes and mins? So we want to make that kind of happen, but instead of leveling off horizontally, they're going to kind of level off vertically. So there's my inverse sine. If you were to ask your calculator to graph you inverse sine, that's what you'd see, and that's it. So inverse trig functions are not periodic. This thing doesn't repeat itself over and over again. So see if you can kind of follow that same structure and do your graph of inverse cosine. You're going to want to just take these 3 points right here, figure out what their x and y coordinates flip-flop them and put them on this graph. So 0, 1 becomes 1, 0. Pi over 2, 0 becomes 0 pi over 2. Pi negative 1 becomes negative 1 pi. The only real point on my tangent is here, but I'm going to go ahead and sketch my asymptotes. My asymptotes were vertical asymptotes before. This time around, they're going to be horizontal asymptotes. And they happen at pi over 2 and negative pi over 2. So I'm making those vertical asymptotes into horizontal asymptotes. All right, so a little bit of mathematical trickery. Are we feeling okay about this? So at some point, mathematicians decided we need inverses for trigs and we need them to be functions. And they're like, well, that's a problem because the inverses of this thing are not functions. If I were to do the inverse of it, it would continue to wiggle up and down, but it would be going upwards like this, and that wouldn't pass the vertical line test. That's not a function. So they decided, they got together, had a little discussion, decided, all right, we'll just chop off enough of my sine to make sure that my inverse is still going to be a function. Same with cosine and tangent. You guys following me so far? This is the background. This is the history. Now we get into the nitty gritty. All right. So inverse sine, cosine, and tangent. Let's talk about domain, range, and then we'll talk about quadrants here in just a second. So tell me about the domain for inverse sine. What is the domain of inverse sine? Would be the same as the range of regular sine, right? What was the range of regular sine? How far up and down did it go? -1 up to 1. So that's going to be our domain for inverse sine. My geometry students are learning trigonometry. Well, they just had their test last week. They killed it, by the way. But I always see this as a frequent question when they're solving for an angle and a triangle and they have to do an inverse. I'll see a student, they'll say, you know, Mr. Hyde, I'm trying to take the inverse sine of something and it's giving me an error on my calculator. What's going on? And I'll look at what they're typing in and they've got 1.56. Do you see why that's not going to work? It's more than 1. That's not in the domain here. It's going to give me a domain area if I try and do this. So as soon as I see them do that, or they're doing the inverse sine, usually this is more what it'll look like. They'll do the inverse sine of, because they got a right triangle someplace and they'll have like 25 divided by 16 or something in there. I'm like, well, that's definitely not going to work because that's bigger than 1. And then I explain to them inverses and how we no, I don't do all that stuff. I'm just like, it's just you got a problem with your fraction someplace, but that's why that doesn't work. All right. What about cosine? It's our domain for inverse cosine. Think about your original cosine. What's the range for original cosine? Same thing. What about tangent? What was the range of tangent? It went all the way up. We had those asymptotes, right? We went way up top. We went way down to the bottom. So the domain for inverse tangent is all real numbers also. And I kind of wish I had room to have this at the bottom of that page. I'm just going to flip that over. Notice that for our inverse sine, the domain is from -1 to 1. We don't have anything outside of that. Same for cosine. But for tangent, the domain is all real numbers. We're going to go in both directions forever and ever. Okay. Now, the range for each of these is going to be those restricted domains that we all agreed upon. Okay, and this choice was arbitrary. It happened a long time ago, but you guys came up with the same conclusions that everybody else did. So they decided that you're never going to get an output for inverse sine outside of -π/2 to +π/2. Because that's where we chopped off our sine so that it would pass a horizontal line test. And for cosine, y'all remember what it was for cosine? 0 to pi is what we decided on. And tangent, and same as, almost the same as sine. One minor difference, and what is that difference again? No square brackets, because why? It doesn't include -π/2 or +π/2, because what's happening at those values? Those are our vertical asymptotes, right? All right. Yes.
So if the inverse is like up top and the periods at the same point, then how would we include both of them? Because would that not pass the vertical test?
Are we talking graphically? Should I flip this over for this question?
Yeah.
Okay. And which graph would you like me to focus on, the original graph or the new graphs? Or these way up here? Or have you answered your question?
No, I think we're good.
Do you want to restate it and answer it for anybody who might be thinking the same thing?
I was thinking of it as like if it was from -π/2 +π/2, like where the bottoms stand, like they move. If it was like, but that wouldn't happen. So
okay.
I was being silly.
Okay. Are you sure?
Yeah.
You're sure? Okay. All right. So question was kind of going back to here, and I think your question was about sort of how we chopped it off. And this does make me feel a little uncomfortable that when we decided to chop it off, we aren't showing a whole period, but there's no way we can show a whole period with sine or cosine and still have the inverse be a function. So we kind of had to make the decision to only show half of a period for both of them. And again, it was arbitrary how we chose that. The main consideration I think that our forebearers had was they wanted to make sure they included the origin in there somewhere. All right. Quadrants. This is where it's going to become important. So this is where we're going to get an opportunity to practice out stuff from 4.1 and 4.2. And remember, I told you that's like half of our test. Okay. That's why I threw a bunch of those problems in when we were learning to graph sine and cosine. So when we think about -π/2 and +π/2, I'm just going to go ahead and draw myself a little XY axis here. Where is -π/2 on my graph? The -π/2 line would be pointing up, down, left, or right? Down. Here's my -π/2. And I can go from -π/2 through 0 all the way up to +π/2. So in a minute here, we're going to be drawing some reference triangles. When we draw reference triangles for inverse sine, we always want to make sure that we draw our triangles in quadrant 1 and quadrant 4. We should never be drawing a reference triangle for inverse sine in quadrants 2 or 3. For cosine, we're 0 to pi. 0 is here, and pi is here. So for inverse cosine, when we draw reference triangles, we're drawing them in quadrants. 1 and 2. And for inverse tangent, we are drawing them in quadrants. Well, it looks like we're 2 and 3 again, but never at pi over 2 or at negative pi over 2. I'm sorry, 2 and 3. Quadrants 1 and 4. Okay. You guys ready for the fun stuff? We're going to be using those 30, 60, 90 and 45, 45, 90 triangles quite a bit here. And again, this is where it's going to really help you to have a really good knowledge of translating between degrees and radians. So when I'm doing the notes today, I'm going to assume that when I'm looking at an angle that if it's 120 degrees, that I know that that's 2 pi over 3. If you don't know that, then you're going to have to do a little bit more work than what I'm showing here to actually do that conversion on paper someplace. Okay. All right. So here we go. We are going to do the inverse sine of radical 2 over 2. Now, first thing I want you to notice is that's a ratio inside of this thing, right? What are we going to get for our output? I'm not asking for a value, but what type of thing? These are side lengths on our triangle. What are we going to get out of here? We're going to get an angle out of it, right? These inverse trig functions are always going to give us an angle, which makes sense because these are angles, right? This is telling us that my answer has to be between negative pi over 2 and positive pi over 2. So I know right now that my answer is going to be between those two values, between negative 90 and 90. All right, so let's set up a reference triangle here. And it's inverse sine, so we know that we are dealing with a reference triangle in either the first or fourth quadrants because sine goes from negative pi over 2 to positive pi over 2. So it's got to be in one of these two quadrants. Anybody want to take a educated guess about which of those two quadrants it's going to be? Top one? How do you know it's the top? Because this is positive, right? So the sign of this right here is going to narrow it down further for you. Since that's positive, that tells us that we're going to be in this quadrant. Now, if that had been a negative pi or negative root 2 over 2, we'd been going down here. So let's go ahead and draw ourselves a reference triangle. And I'm just drawing it as a generic triangle. It kind of looks like this is going to be a 45, but it might end up being a 30 or a 60. I don't really know yet. And remind yourself about your ratios for sine. Sine is opposite over hypotenuse, right? So go ahead and put that root 2 and that 2 into your triangle in the appropriate places. My reference angle is here, so root 2, that would be the opposite. And this 2 would be the hypotenuse, right? Sine is opposite over hypotenuse. Sorry, I didn't leave you much space. If you're a big writer, you might want to have some scratch paper out too. Ooh, those numbers look familiar to me. Which one of our special right triangles is that? 30, 60, 90, 45, 45, 90. That's totally a 45, 40, and 5, 90, isn't it? So this is a 45-degree angle here. Now that also happens to be our answer because if I measure from the positive x-axis to that point, that is going to be exactly 45, right? But we're not going to write 45. So it is our answer is 45. I'm thinking 45 in my head. There's my little thought bubble. But then I'm going to transfer that into radians, and 45 degrees in radians is pi over 4. You were right the first time. I heard pi over 3 somewhere. So 45 degrees is pi over 4. Again, if you didn't happen to know that, then you're going to have to do that thing where you go 45 times 45 degrees, 180 and pi, and then work that all out. And you're going to get pi over 4. We feeling all right so far? We can't wait to do another one. Awesome. Let's do it. All right. Inverse cosine. Cosines. Right, inverse cosine. Let's remind ourselves about the rule for inverse cosine. It's only going to give us angles between 0 and pi. So we're talking about these top 2 quadrants up here for a reference triangle. Which one is it, quadrant 1 or quadrant 2? Focus on the sign of your ratio. Notice it's negative. Where's cosine going to give me a negative value? In 2. Also 3, right? But we can't use 3 because we're forced to stick to these. So because it's negative, we're dealing in quadrant 2 here. So let's go ahead and draw ourselves a little reference triangle here in quadrant 2. And our ratio is 1 over 2. I'm done with the negative on that. I don't have to think about the negative anymore. So just get that 1 and that 2 someplace into your triangle. Remind yourself that cosine is adjacent over hypotenuse. Adjacent to that reference angle would be here. Hypotenuse is here. Ooh, 1 and 2. That reminds me of one of our special triangles. 1, 2. What would the third side be? √3. Was that 45, 45, 9? No, that was a 30, 60, 90, wasn't it? Which means what would this angle here be? Is it the 60 or the 30? It's across from the bigger side, so it must be the bigger angle, right? So this would be a 60-degree angle.
No, it is if the hypotenuse.
Yeah. Okay, yeah, thank you. The question was, shouldn't this be √3 over 2? And we did have a version of that, but in that case, the hypotenuse was 1 and the other side was 1/2. We okay so far? Thank you. Go. Because it's negative 1/2. Where do you, so that's a great question. Should this negative end up in the triangle someplace? So my short answer is no. We ignore it. The negative helps us figure out what quadrant it's in, and that's all we do. A bigger question though, a better answer would be, where would I put it? Would the negative be on the 2 or on the 1? And we're really dealing with like lengths and triangles, so negatives. So there is a way that you can think about one of those 2 things being negative for sure. I just leave it out though. I make sure the negative helps me. Negatives and positives help me get it in the right quadrant. That along with the rules on what quadrants they're allowed to be in, but then I leave the negative off of it when I put them in there. So I will never put negatives in a reference triangle, even though there's a negative in here. That's a great question. Thank you for that. All right. 60 is not our answer though. And pi over 3 is also not our answer. We need to give the angle that would get us from the positive. So that in degrees, that would be a 120-degree angle. But we don't want degrees, we want radians. For those of you who have not learned this yet, or who are studying, there are some good tricks for this. Is 120 divisible by 60 or 30? Yes. What's the bigger one? 60. How many times does 60 go into 120? It goes in there 2. 60 goes into 120 2 times. So this is 2 60s, right? 2 60s. Now 60 is pi over 3. So if you know that 60 is pi over 3, this is 2 pi over 3s. And that's how I know that this is 2 pi over 3. So my thought process for 120 is equal to 2 times 60. And I know that 60 is pi over 3. So if you can memorize that 60 is pi over 3, that 30 is pi over 6, and that 45 is pi over 4, you can use this little trick to figure out radians really quickly. Or you can always do it the long way. All right, let's keep going. Oh, look at this. Look at me throwing a not rationalized. I don't know. It's probably pretty disappointing to you. Sorry about that. I'm going to tell you that when we get to our test, if I'm doing inverses, I may throw some not rationalized stuff in there, and that's to make it easier. Okay. If I had, well, let's do this as it is, and then we can talk about it if I'd made it kind of a little bit higher level. CWU folks, you're probably not ever going to see a problem like this. I did this purposely, and I did it to make it a little easier. All right, tangent we're dealing with this time. So let's talk our way through our reference triangle here. What quadrants are available to us for inverse tangents? 1 and 4. So we're going to be in one of these two quadrants. And which one of those quadrants is going to be determined by the sign on my ratio? The fact that this is negative, tangent's negative in this quadrant. So I must be talking about this quadrant. I'm going to go ahead and draw myself a reference triangle there. Reference angle would be right here. And I know the tangent is opposite over adjacent, so I can fill in where the 1 and the √3 would go in my triangle. Opposite and adjacent to this angle, opposite would be here. Adjacent is here. One and √3, that makes me think of a 30, 60, 90 triangle, doesn't it? What would my hypotenuse be? 1, 2, √3, totally. Is this the 30 or the 60? It's the 30 because it's across from the smaller side. So this is a 30. But 30 is not my answer. We always have to start from the positive x-axis and rotate around till we get to that line. And the fact that I'm rotating that direction means that my answer is not going to be positive, but negative, right? So my answer in degrees is negative 30 degrees. Convert that to radians, we got negative pi over 6. What a great question. Question was, could I write this in positive format? So could I have instead gone all the way around here and said 11 pi over 6? What do you guys think? Is my answer allowed to be 11 pi over 6? I'm scrolling up here. Is my answer allowed to be 11 pi over 6? No, the answer is no, because why? Because we've cut off our range from negative pi over 2 to positive pi over 2. So 11 pi over 6 is not a viable answer because, remember, we had to chop some stuff off to make the inverse into a function. All right, I want you to try the last one on your own. See what you can do with this last one. You guys got this. You're getting the hang of this. Okay, try and do as much as you can on your own. I'm going to work through silently up here, so feel free to glance up here for a hint, but don't just copy me on this one. For those who are interested, in particular my CWU folks, I'm going to work through that third example, but I'm going to work through it without the rationalized value. So this is the same thing. 1 over root 3 is the same as root 3 over 3. So if we had gotten this instead, I still would have said, oh, it's inverse tangent, which means I'm in these two quadrants. I still would have said, oh, it's negative, which means I'm in this quadrant. I still would have drawn my reference triangle here, but my reference triangle would have some different values. It'd have a root 3 and a 3 on it. And that's not super familiar to me because I didn't make you memorize that. Okay, so what are we going to do here? Ideas? Say again. Find the other side. Yeah, but that's not one of the ones we memorized, right? So I could find the other side. Ultimately, I've got to come up with this angle right here. So we got a couple options. One, you could memorize a third version of your 30, 60, 90, 45, 45, 90 triangles. Here's what I would do. I would say I've got 3 and root 3, right? Those are the two values that I'm seeing on there. Let's divide them both by root 3. This is just 1, right? And 3 over root 3 should just be root 3, correct? Because root 3 times root 3 is equal to 3. So that's 1. This is root 3. So this is root 3. And this is 1. Okay, that's a 30, 60, 90 triangle. So that's going to be that's my favorite way to get around this problem. If I ever end up with a 3 and a root 3 in my problem, I know just to divide everything by root 3. All right. Again, my promise to you right now is that on the test, for any problem involving inverses, I reserve the right to give you a not rationalized value to make things easier for you. Okay. I still expect you guys to give me rational answers on the rest of the tests. I might have a non-rationalized value on here, and that's because it's going to make it easier to do your reference triangles. You guys okay with that? Awesome. All right. This is where this gets super fun. I love this part of this. Inverse functions are supposed to cancel each other out, right? Isn't that the whole idea of an inverse? It does the opposite. If I ask my geometry students about this right now, they're familiar with inverse cosine, and they're familiar with cosine. And in my higher achieving geometry students would say, I've never seen this 4 pi over 3, but that's okay because I know these two things are going to cancel each other out. What would they say the answer is going to be? They'd say the answer is going to be 4 pi over 3. And can anybody in here tell me why my answer is not allowed to be 4 pi over 3? What are we thinking? What are you thinking, Bishop? Yeah, we're taking the inverse cosine of something, right? What are we allowed to get for answers for inverse cosine? 0 to pi. Is 4 pi over 3 between 0 and pi? So there's no way that can be my answer. Okay, so you look at this and you think that the answer would be 4 pi over 3, but I'm going to tell you it's not. All right, does that bum you out? Nah, it's not a big deal. So this is one of those 2-for problems. We get to just work out 2 different problems. It's not a biggie. So when we do these, when you have these kind of nested ones, start from the inside and work your way out. So my first step is going to change this into cosine inverse of, I don't know, I'm going to figure out what cosine of 4 pi over 3 is, and then put that value in here. Just kind of substitute something simpler in there. So 4 pi over 3, let's think our way through this. Now, pi over 3 is how many degrees? Pi over 3 is 60. So 4 pi over 3s would be the same as 4 60s. 4 60s is 240. Can you graph me 240 on your unit circle? What would 240 be? It's bigger than 180. How much bigger than 180? 180 plus another 60. Draw me a reference triangle. Now, before I go any further here and put numbers on that triangle, let's think about that quadrant and the fact that we've got a cosine in that quadrant. We should know right now whether this is going to give us positive or negative answer. The cosine in quadrant 3 is positive or negative? Negative or positive? Cosine is, okay, so it is going to be negative. Definitely going to be negative. All students, so tangent's the only one that's positive in this one. All right, 30, 60, 90 triangles. We got this. This is short side is here. 1, 2, root 3. And cosine is adjacent over hypotenuse. So that's going to be negative 1/2. So I basically just figured out that this thing is equal to negative 1/2. So we still got that inverse cosine on the outside. We just got rid of the cosine on the inside. Now we just got to do this. We've done a bunch of these. Why don't you practice again for me? Think about where cosine needs to be. Inverse cosine. Which quadrants are available to us? That's 0 to pi, so it's got to be one of these two quadrants. Where are we going to put our reference triangle, though, if our ratio is negative between these two quadrants? Where is cosine negative? And this one. So we want our reference triangle here. Got an angle there. 1 and 2 go where and where cosine is adjacent over hypotenuse. Adjacent's here, hypotenuse is here. Oh, 1, 2, root 3. Nice. That's got to be a 60. But 60 is not our answer. Remember, we got to get from the positive x-axis all the way around. If that's 60, then that means this must be 120. (120) in radians, that's 260s, 2 times 60. 60 is pi over 3, 2 pi over 3. Question. You know what? I haven't done this at all throughout this sheet in any of these examples, so I should probably do it here. I'm going to go ahead and now everything here is in radians. So I'm going to make sure I'm in radians in my calculator here. And I'm just going to type this in and then see what decimal I get, and then I'll type this in and see if it matches. Let's make sure we're doing this right. I'd feel pretty awful if I'd been telling you how to do this the wrong way this whole time. So I mean, just for my own peace of mind, make sure that I'm not lying to you. Pretty sure I'm not. All right, that's what my calculator says. I came up with 2 pi over 3. I don't know why I put that parenthesis there. Hey, nice. All right. Can I get your attention up here for a sec? We could do this the same way that we did. We could find the inverse tangent of -1 first and then take the tangent of it. Okay. But I'm going to tell you that we don't need to for this one. We have a little shortcut for this. You think it's 1 or you think it's -1 for our final answer? So I want you to think about this analytically rather than mechanically like we did here. If I do the inverse tangent of -1, inverse tangent's got to be in one of these two quadrants. What quadrant am I going to end up choosing? Quadrant 4. Okay, and I'm not going to bother putting any numbers in there, but there's my reference triangle, correct? And when I get it, I'm going to end up getting this negative angle right here. Is there anything wrong with me putting that negative angle into a tangent? No, nothing at all. And if I do that, I'm going to get the same reference triangle back in the same quadrant. And since it's tangent, then it's going to end up being the same ratio. And since it's in this quadrant, it's going to be -1. So the reason that the reason we couldn't rely on these two things canceling was because inverse cosine has some restrictions on what types of answers it can give you. Tangent has no such restrictions on that. Okay, tangent can be anything. Now, if I do my restrictions on here, that's fine. This is going to limit where I can draw this triangle, but there are no restrictions here. So if your regular functions on the outside, they will just cancel. The only time you have to worry about it potentially being something different from this is when your inverse is on the outside and your other functions on the inside. Now, if I were doing this on the test, I would probably go through that process that we just looked at. Okay, but if I'm short time on a test, then make a good guess. It's -1, and it does end up being -1. Now this one, we cannot do that. Have you all seen this notation before? Arc sine? It is an old-fashioned way to say inverse sine. So you're going to see some of that in your book. You'll see arc cosine and arc tangent also, and it's just kind of like your grandfather's arc sine, or your grandfather's inverse sine. These young whippersnappers calling them inverse sines. We used to call them arc sines back in the day. What's that?
Have it in the book.
Well, and I think it's not just a generational thing. That's not entirely accurate. It's both regional and it depends on like what field you're in as well. What fields would they see arc sine? I'm mostly familiar with, actually, engineering. We used them pretty interchangeably. In programming, they call it asine and asyn and acos and atan because of that arc. Most programming languages will use that. So no shortcuts here because, well, for one thing, if the inverse is on the outside, and that's the thing with the restrictions. But also these don't match up, right? They're not both sines or they're not both cosines. So no way we can do any shortcuts here. So we're actually going to have to go through the whole process. I'm going to tackle finding the cosine of -5 pi over 6 first. So I'm going to go ahead and think about where -5 pi over 6 is. Now, if you can convert this into degrees in your head really quickly, think of that as pi over 6 times 5, and pi over 6 is 30. So -150, right? 5 times 30 would be -150. I'm going this way though. So I'm going to end up here exactly 30 degrees short of 180. And keep in mind, I'm doing a cosine in this quadrant. Is my answer going to be positive or negative when I do a cosine in this quadrant? Negative answer. So I'll go ahead and put that negative in here so I don't forget it, because I do that a lot. 30, 60, 90, that's 1, 2 √3. And cosines adjacent over hypotenuse. I'll show you another little shortcut here. Once you've got this triangle drawn, on doing the last piece of it. Actually, never mind. That shortcut does not apply to this situation. So now I got to go through my process all over again, but with the inverse sign. Inverse sign's got to be in one of these two negatives. So this one. √3/2. Which makes this reference angle a 60. Which makes my answer -60 degrees, or
They're gonna want it in radians.
yeah, we always went these in radians. What's going on here? Okay, so this gets a little bit technical, and you got to really know your business when it comes to degrees and radians. The more comfortable you start feeling with that, the better this is going to be. We're getting close to the time of the test. So for those of you who are feeling pretty confident with the material up to now, you might consider maybe spending a little bit of time every time you sit down and do your homework, maybe spend 5 minutes trying to really get yourself confident going between degrees and radians. I got those practice quizzes up on the Canvas page for the practice memorization quizzes. If you spend a little bit of time with those before you started on your homework, it might make your homework go a little bit faster. And if you're doing that repetition, it might cement that. This is going to be another one of those things that's really going to help you in the next unit as well. The main reason I'm having you do this memorization is because of chapter 5. Okay. I didn't even start it until chapter 5 last year. So for most of my students, though, that's the sticking point. The big stuff that you got to know, right? If we think back to what do we really need to know to be able to deal with these inverses? And the big thing that I really need you to know is, where did we decide to cut it off? For sine, we're only going to give answers between -π/2 and pi. For cosine, we're only going to give answers between 0 and pi. And for tangent, inverse tangent, we're only going to give answers between -π/2 and pi/2. So as long as you know that information, and I think I said pi instead of pi/2 for this, but you know what I mean. That's the key information. That's really the new stuff. You guys have been making these reference triangles. We did a whole bunch of those back in 4.1, 4.2, 4.3. So those should be getting fairly confident with those. So, did anybody have any questions? What's the toughest part of this? Is it the radians and degrees piece? Is it the reference triangles piece? Is it knowing what quadrant to put it in? Those are kind of the 3 big things that you need to be comfortable with to be able to pull this off. Last year, I put a bonus problem on the test that was something like, it wasn't this, but it was like the tangent of the inverse sine of the cosine of the inverse tangent of the secant of, I can't even remember, like 7π/4, something like that. It was something like that. It was nasty. It was nasty, but it was one of those ones that just like, you got to start from here and just work your way to the outside. It's totally doable, but you end up drawing like 5 or 6 reference triangles. And it's not, I'm not telling you that to like make you nervous. This is a bonus question, right? This is for like the people who are done, and I didn't want them to be bored for the rest of the period. So it was only worth a couple of points, but I think a couple did. A lot of people didn't have time. Didn't really have time to spend on, or they chose to spend that additional time going back and looking for mistakes, right? And it's really easy to make mistakes. You put stuff in the wrong quadrants. You forget to think about positives and negatives on stuff. Like, there's lots and lots of places to make mistakes. All right, that's what I got for you for today. Do not have spelling check homework again. We are reviewing